From time to time in this series, we slip in an easy one. When we do that, we invite our friends who are not geophysicists to listen in. So, geologists, well log analysts, petroleum engineers, welcome back. All we shall try to do in this module is to give you a good feeling for what goes on in the field and for the realities of field work. But I have to wag my finger at the geophysicists and tell them that only the video is easy. The manual for this module is rather long and rather full. So don't forget the video first, and then the manual and the questions, and if you're irrepressibly keen, then the appendix. Okay, then we all remember what happens.
Starting from lines marked on a map, the surveyor lays out the lines on the ground and marks off each shot point along the line. The driller drills a hole. Then he or the shooter loads the dynamite. The shooter hooks up to the blaster, and we make a bang. And we listen for the echoes. With this, a geophone.
Let us never lose our sense of wonder at all this. Oh, certainly we make a big bang, but think how far it has to go. We get reflections from 10,000 meters. That's 10,000 down, 10,000 back. 20 kilometers or 12 miles altogether. And then think about all those thousands of geological interfaces, the rock contacts that it has to pass through along the way. You see, we're caught between two stools. We want most of the bang to pass through those reflectors so that it can reach the reflectors below. But if most passes through, it follows that only a little can be reflected. And it's that little that we must work with at the surface. That's what arrives at the geophone. The actual displacement of the surface of the Earth in response to a deep reflection is typically 10 to the minus 10 meters, 5,000 times smaller than the wavelength of light. So let us keep our sense of wonder. These tiny, tiny displacements we have to detect and measure in the presence of all the noise going on at the surface. We shall find that much of our field technique is concerned with this problem of minimizing the noise. Minimizing the noise and so giving us the best possible chance of detecting these weak reflections coming up from great depth.
The first thing is to be sure that the geophone is really planted in the earth. This won't do at all.
And neither will this.
But we have to be practical. There are times when we just cannot get a good plant into the earth. We just do the best we can.
If we have a choice between here and here, then of course we choose the place which gives better contact with the earth and least noise.
If we have to plant it here, then we do what we can to make it less noisy.
But we have to be practical. Sometimes there isn't enough wind to make it important, and sometimes it's impossible.
Certainly we would avoid this, having the wire touch the case.
Or this, having the motion of the flag sent right to the geophone.
But we have to be practical. Sometimes we have no choice.
We try to avoid power lines because they generate electrical noise in the geophone and the cable.
So we cross the road where we can.
But we have to be practical. Sometimes we cannot escape from power lines.
If the wind is blowing the sand, which would sound like a hail of shot at the geophone,
we may have to bury the geophone.
But we have to be practical. That takes time, and time is money.
If we are working through cattle, and cattle are intrigued by geophones,
then we'll have to post someone there to herd them off.
But we have to be practical. That someone must be paid. More people, more money.
If a truck comes rumbling by and we're ready to shoot, then we just wait for it to pass.
even though that costs us a little time.
But we have to be practical. Sometimes there's nothing we can do. So when we plant a geophone, we do what it is practical to do, to give us a good firm contact with the earth and minimum noise. But that minimum noise is still far too much for the deep reflections. We need other ways of improving the signal-to-noise ratio.
The first of these we have already met, the use of multiple geophones in a group. Remember what we said in an earlier tape. A single geophone hears not only the trembling of the earth due to the reflected bangs, our desired reflection signal, but also the swishes and swipes of the leaves blowing in the wind, an undesired noise. If we use several or many geophones, all connected together, the signal coming up from below is the same for all of them, while the wind noise is different from one geophone to another, particularly if we space the geophones out a bit. The group improves the signal relative to the noise. So, in practice, we connect 10 or a dozen geophones together to the same pair of wires in a string. Then we typically lay out 2 strings of phones, one each side of the flag, to form the group. And then we connect the 2 strings, with a connector which cannot be connected the wrong way round, to the cable which goes to the recording instruments.
Rule of the industry. If it can be connected backwards, it will be. Don't let it happen.
How far apart should the geophones be? Just far enough that they receive different noise. If the noise is from individual leaves blowing in the wind, this spacing may be enough to do it. If the noise is from distant trucks, the spacing may need to be more like this. The important thing is always that the ambient noise should be different at the different geophones, whereas the signal, the reflections coming up from below, is the same.
And do the geophones need to be in line? No. The important thing is lots of geophones, each far enough from all the others to receive different noise. So the area of the group is the key.
But as we see, the geophones often are planted in line. Not always, but often. This is because planting them in line can serve 2 functions: improving the signal relative to all that ambient noise, and improving the signal relative to the surface waves.
Ah, yes, surface waves. These things. We're looking down on the surface now, looking down on the shot point. And there go the surface waves, slowly rolling out on the surface from the shot point. Ground roll, we call them. Slow waves, but often of very large amplitude. So here we are, trying to detect those tiny, tiny reflections coming back from deep in the earth, in the presence of great lolloping surface waves spreading out from the shot along the surface. As far as our deep reflections are concerned, these surface waves are just more noise. Shot-generated noise now, rather than ambient noise, but still disastrous.
So what do we do?
If we plant a single geophone here at the flag, the geophone goes up and down as the surface wave passes across it. The output from the strong surface waves dominates, indeed swamps, the output from the weak, deep reflections. So, instead of the single geophone at the flag, we plant a number of geophones, all connected together to have a single output over one wavelength of the surface wave. Now, for every geophone which is going up, there's another which is coming down. After this cancellation, there's much less output from the group of geophones as the surface wave passes across them.
When a geophone group is arranged like this, over a length calculated to cancel the surface waves, the group is often called an array.
So any arrangement of the geophones in a group improves the reflections relative to ambient noise. But the arrangement in line, in an array of the appropriate length, also improves the reflections relative to surface waves.
Which is why we see what we see. The jug hustler plants the first geophone of the array, walks a few paces, plants the second geophone, walks a few paces, and so on.
You said jug hustler?
So I did, but then everybody does. A geophone is called a jug, and the guy who plants them is a jug hustler.
On our cruise, a juggie.
Okay then, a juggie. Some of them local lads, some of them moving from place to place with a crew. Perhaps the odd graduate student getting some field experience. Perhaps the odd ex-convict working out his parole, but all open-air people, tough and hard-working. As you see, this is a long array, 100 meters, suggesting that the surface waves here have a long wavelength. There's the last jug. The array is from here to here. An inline array, a linear array, 100 meters long.
Sometimes in open country, we use several parallel lines of geophones. That way, we use the length of the array to fight the surface waves, and the area of the array to fight the ambient noise.
So, to quell noise, we add geophone outputs which have the same reflections and different noise. The first method of doing this is multiple geophones in a group. Or, if the length of the group is chosen to suppress the surface waves also, then we may call the group an array. Now, the second method is multiple sources.
If one bang is not enough, we can use several. We can even space them out in line to get the same sort of suppression of the surface waves which we got with a geophone array. Now we have a source array also.
That gives us an idea. We can set off all the charges simultaneously. Or we could do it sequentially. For each bang, we would get a separate record, and then we could add the records together. This we call vertical stacking, or vertical summing.
So we can improve our signal-to-noise ratio both with multiple geophones and with multiple sources. If we consider the reflection signal we get from one shot into one geophone...
That looks familiar, the Grand Canyon.
Yes, but then we're not considering noise. Add the noise, and we can scarcely see the reflections anymore. But at another geophone, spaced apart a little, the noise is different. At a third, different again. At a fourth, different again. So if we add the outputs from these geophones and the others in the group, we get an improved version. Comparing the noise-free signal with the output of the group, we see that there is still some noise, but at least we can now see the reflections.
Equally well, we could consider just one geophone recording different shots. These would be our separate recordings, one for each shot. Then if we vertically stack, we again obtain an improved version.
In the case of the geophone group, the addition occurs merely because all the geophones are connected to the same pair of wires.
But in the case of the several shots into a single geophone, the addition has to be done in a special summing unit or in the computer.
In the case of the geophone group, the noise is different from geophone to geophone because they are in different places.
But in the case of the several shots into a single geophone, the noise is different because the recordings are made at different times.
Both methods of quelling noise add geophone outputs having the same reflections but different noises. Both these methods of improving the signal-to-noise ratio are very important. Multiple geophones in a group we use almost always. Multiple sources we use occasionally simultaneously. And very often, both simultaneously and sequentially. Here, for example, we see 3 big bang machines, truck-mounted air guns, which make their bang at the surface, 3 of them simultaneously. Then they move a little way and do it again, and again, building up a source array with multiple shots from multiple sources.
A very important example of this is vibrosize, the most popular system for working at the surface. But that is another story. We shall come to it in video module GP308.
So we turn now to another very important field technique, common midpoint stacking. The basic principle is the same. Add geophone outputs having the same reflections but different noise. But now, to get those different versions of the reflected signal, we do this. Version number 1 the one we've considered all along, source and geophone fairly close together. The only change we'll make is that we'll replace our single geophone by many geophones in a group. Now, version number 2. We move the shot point to the left and the geophone group to the right, but keeping the same midpoint between shot and group. Version number 3. The shot to the left, the group to the right. Again, increasing the distance between shot and group, but keeping the same midpoint. Now we have 3 versions of the same reflection information, made with the noise observed at different times and at different places. Further, since the shot-to-group distances are different, the surface waves are different also. So if we add together the reflection signal obtained from this shot into this group, with that from this shot into this group, and with that from this shot into this group, we can build up our reflections and suppress both the ambient noise and the surface waves.
Of course, since the shot-to-group distances are different, the lengths of the reflection paths are different. Therefore, we have to adjust the reflection times in processing to compensate for these different path lengths. We shall talk about that in later modules. For the present, the important point is that common midpoint stacking gives us another method, and a very, very important method for improving our reflections relative to everything else.
Now, how should we do it in the field? We remember that the basic scheme of seismic work is this. Measure the reflection time here, then move a little way along the line, and again, so that we build up a picture of the structure along the line.
Now we are saying that in each of these locations we must add additional measurements.
So we could do just that. Plant this group and record this shot. Then move the group to here and record this shot. Then move the group to here and record this shot. That would give us a common midpoint stack at this midpoint.
Then we could move the whole arrangement down the line. Move the group to here and shoot here. Then move the group to here and shoot here. Then move the group to here and shoot here to get a stack at this midpoint, and so on.
Hold it. We could do that, but it would be crazy. Altogether too much moving around. While we were doing that, you see, we recorded this shot into this group. And then sometime later we came back to this shot point and recorded another shot into this group. And then later again we came back and recorded a third shot into this group. All of that we could have obtained by planting 3 geophone groups and shooting just one shot.
And there is the key to what we actually do, our standard field technique. Because shots are expensive and groups are cheap, we always record many groups from each shot. In fact, the easiest way to get 3 versions of the reflected signal at each observation point along the line is to record 6 geophone groups from each shot. This is the first shot into the 6 groups. When that is safely recorded, we then pick up the rear group and lay it ahead beyond the far group. The second shot. With that safely recorded, we again pick up the rear group and lay it ahead. The third shot. Record. Pick up the rear group and lay ahead. The fourth shot, and so on.
Now, if we consider any point on the reflector, say this one, we have one version of the reflection from this shot. And a second version from this shot. And a third version from this shot. The next point on the reflector has one version of the reflection from this shot. A second version from this shot. And a third version from this shot.
And so on for successive points on the reflector. Always 3 versions of the reflection, always with different distances from shot to geophone group. The three versions give us what we call multiple coverage. In this case, threefold multiple coverage.
And we see how to get it. Lay a spread of geophone groups equally spaced along the line and fire the first shot. Then pick up the near group, lay it ahead, and fire the second shot. Then pick up the near group, lay it ahead, and fire the third shot. And so on. Let's watch it in action.
First, we lay the cable to connect our many geophone groups to the recording setup. If we're lucky, we can do this from a cable truck.
For cross-country operations, however, we'll probably have to do it the hard way.
One section of cable typically extends over 2 or 4 group intervals. Here we'll say 2.
Then we connect a second section to the first, using special plugs and sockets, and lay the second section.
Which gives us this,
And onwards,
giving us this,
and onwards.
to the horizon.
At some suitable place, we set up the recording truck and connect the cable to it.
Like so.
Meanwhile, the juggies are laying the groups, planting the strings of geophones and connecting them to the cable.
Thus.
When all is well, we fire the first shot.
And that first shot gives us this.
With the geophone outputs recorded on tape, we disconnect the near geophone array from the recording instruments and connect a new array ahead.
Now we can pick up that disconnected near array and lay it even further ahead.
Meanwhile, we can take the second shot.
Giving us this.
Then, the same again.
And again, all day.
From this succession, you remember, we shall later be able, in the processing, to select those combinations of shot and geophone group which yield a common midpoint family.
Do you see how everything rolls along the line? The shot and the spread roll along the line, and the common midpoint family is in there rolling along with them. This Module 301 on fieldwork has 3 tapes. For the second, 301B, we stay entirely in the field and find how all this works out in practice on land crews. For the third, 301C, we go offshore and find how it all works out on marine crews.
This program has been sponsored in part by the following companies: Agip, Aramco, City Service, Dome Petroleum Limited, Gulf Oil Corporation, Mobil Oil Corporation, Phillips Petroleum Company, Standard Oil of California, Texaco Incorporated. IHRDC and these companies, by their sponsorship, do not in any way guarantee or represent the accuracy of the content or methods contained herein. The user hereby agrees to hold IHRDC and the sponsors jointly and severally harmless from any and all damages, including legal expenses, which may arise from the use of this program. No portion of this videotape may be reproduced without the permission of IHRDC.